Okay, let's talk about Le Chatelier's principle. So, factors affecting equilibrium is the next topic, and to discuss this, we're going to talk about Le Chat's principle, as I've heard it referred to most often, because people like to avoid saying this difficult name. Basically, it states if a stress is applied to a system in dynamic equilibrium, meaning the forward reaction and the backward reaction are both proceeding at the same rate, okay, it is in dynamic equilibrium, the system changes in a way that relieves the stress, okay? So if you add a stress to the system, it will react in such a way to relieve the stress. Okay, and these three things are concentration, temperature, and pressure. Let's discuss each of these individually, starting with concentration. Let's say that we have a reaction that goes from A to B and back from B to A. Currently, this reaction is at chemical equilibrium. What happens if we add more of the reactant A? Well, if you add more here to this scale, obviously it would throw off the equilibrium. Now, Le Chatelier's principle states that the equilibrium shifts to relieve the stress. Which way will it go now? Which way will it favor? And you can see that it would favor producing more B to get it back to a state of equilibrium. So it will shift to the right, favoring products. I always like to use this analogy with the scale because it makes more sense to me. If you add more concentration, literally adding more mass, then it will shift to the other side to relieve the stress. Okay, likewise, if one of the species in this equilibrium, one of the compounds is removed, the equilibrium will shift to relieve the stress in a similar fashion. In this case, the reaction will shift to the left. If you take some of these blue A off, then it will shift to produce more of it to get it back to equilibrium. Okay, the next one is temperature. Temperature, you have to remember that there are two possibilities for reactions. There's endothermic reactions, which require heat. Okay, a change in heat, represented by delta H, could be something like 100 kilojoules per mole. Okay, heat would then be on the left side because it's required. Okay, and that should make sense. If you require something, it needs to be considered a reactant. Likewise, exothermic reactions produce heat, and that is represented by a negative value for the change in heat. Okay, so this is positive, and this is negative. Heat would then be considered a product in exothermic reactions. You don't have to balance this heat because it's not necessary due to the law of conservation of mass, but it is there still. Okay, so consider heat as just another reactant or product, and it makes a lot more sense. You can see it the same way as we just did with concentration. And the last one is pressure. Remember, volume and pressure are inversely proportional. That means as volume increases, pressure decreases. They're inversely proportional. And as volume decreases, pressure increases. And this thing does not want to work today. Anyway, so they are always opposite. And this is only true for gases because liquids are incompressible they cannot be compressed, so they're not really affected by pressure so much. And solids definitely are not. Okay, so let's look at a few of these with another analogy. I like to use balloons for this one. Let's look at this equation where we have 2 water molecules, or 2 moles of water, in gaseous form. So this is water vapor, and it's at equilibrium with the things that make it up, which is O2, which is a gas, and 2H2, which is also a gas. Remember, both of those are part of Brinkelhoff. So if we have a balloon at a certain pressure, okay, represented by this gauge here, reducing the volume, right, squeezing the balloon would increase the pressure, right? And that's represented by this gauge pointing that way. The reaction would then shift, favoring fewer particles. Okay, so how would you even know this? Let's look up here at the equation and look at the molar ratios. There's an implied 1 here, so on this side we have a total of 3 moles of gas, and on this side we have a total of 2 moles of gas. So which way would it favor? It would favor the fewer particles, which would shift it back this way toward producing more water vapor. And you can see that by the relative number of blue versus green. And it returns the system back to where it originally was, right? This pressure is about the same, even though the volume changed. It's kind of a neat idea. Let's look at another example. This is the opposite. Increasing the volume would decrease the pressure within the balloon, correct? So we have an initial pressure here. We decrease it by making the balloon bigger. The reaction would then shift, favoring more particles. And we said earlier that there's 3 moles versus 2. That is the ratio. So it would shift to the right, favoring more gaseous particles. And as you can see, the gauge would be about the same as it was before these additional stresses. Okay, let's review. What are the 3 factors that affect chemical equilibrium? Did you get these? Concentration, temperature, and pressure? Go ahead and watch this video. This is from Professor Dave again. I used his examples in this PowerPoint. I'm sure he won't mind. And then we're going to practice with just a traditional practice, and you're going to determine which way the equilibrium will shift to relieve the stress according to Le Chatelier's principle. Okay, and I will have a video that you can check your work on there. All right, as always, let me know if you have any questions, and I'll see you next time.